Good morning, dear students. On the previous lesson, we started differential equations, and today we will continue. We will have even two practical lessons, and we will start with higher order differential equations that allow for a reduction of the order. Actually, let me remind you the order of the differential equation. So it is so how to define the order. Uh, so the order of the differential equation is the order of the highest order of the derivative that it contains. And in this case, the highest order is 3. So this is the differential equation of the third order. So this is the simplest case of the higher order differential equation because it has only derivative and expression that depends on x. So how to solve it? We will just integrate 3 times. So now we will find the first integral. So we will reduce to the second order. And we will integrate this 1 over x. So it will be equal logarithm of x plus c. Then so now we will find the third the second integral. So it will be derivative of yeah, by the way, don't forget that yeah, so here is arbitrary constant c1. So with index c1, actually the number of arbitrary constants equals the order of the differential equation. So here we will have 3 constants. So now let's find the first the derivative. Okay. Let's find the integral of this part. So we will find the first derivative. And let me remind you how to integrate by parts. Yeah, actually, we will calculate integral of the logarithm separately. So integrating by parts, reminding you how to do it. Yeah. Bogdan, thank you for the question. Oh, David, sorry. Yeah, I a little bit so sleepy. Okay, yeah, let me make an attendance. I will create it for you. But yeah, first of all, let we finish this exercise, and after that we will do. So then v equals x. So having the following expression, so x by logarithm of module x plus the following integral. So just dx. So we have x logarithm of module x plus x. And the answer will be, the y prime will be equal x logarithm x module x plus c1x plus c2. And now finally we'll find y. So y will be equal integral of the whole this expression. So which integral is interesting for us here is integral of x by logarithm. So again, it will be integrated by parts. Okay, if v equals dv equals x dx, so v equals 1 over 2x square. So we're having 1 over 2x square logarithm of x plus stop, minus. Yeah, and by the way, here minus as well. So it was a mistake. So be attentive with the signs. Actually, this is also so for me as well. And here I have x dx. So receiving the following integral, here minus 1 over 4 x square. So the final answer will be the following. So 1 over 2x square logarithm module x minus 1 over 4 x square plus, so integrating this part, plus 1 over minus, of course here, yeah, because here must be minus 1 over 2x square plus 1 over 2 c1x plus c2 cx square, by the way, plus c2x plus c3. And also let we simplify a little bit. So I will just simplify this expression. So we will receive minus 3 over 4x. And it will be enough for now. Actually, this answer is acceptable. Maybe any questions about this exercise? If no questions, I will create attendance for you, and we will go next. So just a minute. Okay, so now you can mark your attendance, and now we will continue the lesson. So let me share my screen again and continue solving differential equations. We will skip B. Actually, yeah, it will be your home task. It was, I wrote 2A, but it was 1A. So we will go to exercise C. B is even simpler than A, so you will have to integrate just 2 times, but analogical integrals, so no need to waste time now. And then at home you will, of course, practice. So now we have the following form of the differential equation. So we have, first of all, we have the differential equation of the second order. So here, as we can see, we have only, so we don't have derivative of the zero order. So I mean, we don't have just variable y here. So we have only y prime, y2 primes, and x. So as we don't have the just y, so we can here reduce the order of the differential equation. We will do the following substitution. So y prime will be equal p. So we will use such parameter. So actually p is a function from x that depends on x, and now we will now just reduce the order with using this function. So y prime equals p, then y 2 primes equals p prime. So we will substitute everything into the equation. So 1 plus x square p prime plus p square equals 0. So now we will, so actually what we received, it is the equation with the separable variables. So let we start, so let we separate variables and integrate. So dp by dx. And here actually, yeah, let we also move p square into the right part. So now, yeah, so continuing separating variables. So what do we have? So dp over p square equals dx over minus dx over 1 plus x square. So separated variables for now. And now let we integrate this equation. So both these parts will be integrated. Stop. I lost 1. So it was a mistake here. Then minus p square minus 1. So I have the following expression here. So here will be p square plus 1, and here p square plus 1 as well. So now everything is correct, but I just saw that something is not okay. So not as expected, but now everything is okay. So actually this integral will be equal arctangents, and this as well. So arctangents of p So arctangents of P equals arctangents of X plus C plus C1. So now that we explicitly express P, so P will be equal tangents of arctangents X plus C1. So Y prime will be equal this expression. So we found the first integral, and now we need to find the second integral. So Y will be equal the integral of this expression. Yeah, so not really convenient for integration, but yeah, let me, so we will uh, transform this expression with using formula of tangents over the sum. I actually don't really remember the formula of tangents of the sum, but it will be reminded. So tangents A plus tangents B minus 1 over the product. Okay, so let we use this formula. So here in the numerator, tangents over tangents X plus tangents of C1 and 1 minus tangents over tangents X plus tangents C1 multiplied by tangents of C1. So tangents over tangents X actually equals X. So this expression will be simplified. So not so strange as we thought before. So now we received the rational fraction. So how to integrate it? Yeah, let we split it. So let we expand it. So here will be X. And here I will remove tangents of C1. So we calculate the first integral. So this one, so it will be equal. Yeah, first of all, we need to extract the whole part. So 1 minus x. Yeah, we need to divide by the tangents of C1. So I will just, yeah, I will simplify this expression. And yeah, minus here. And plus and minus 1. And plus this integral. So now something will be simplified. So this expression will be equal, so this integral will be transformed to the following form. So here just, so first of all dx and plus actually plus 1 of tan. So we will receive the following integral. So tangents of C1 plus 1 over tangents of C1. So now we will integrate everything. Okay, so here we have minus 1 over tangents of C1 x, and here minus 1 over C1, and also, okay, let me use this formula. So I will simplify this expression a little bit. So we divide by 1 over tangents of C1, and here is square. And this is a logarithm of module of this denominator. And plus C2. So the final answer will be the following. So y equals this expression, and this is the generic solution. Any questions about this exercise? Okay, if no questions, let's uh, solve one more exercise. So 1D. So we have the same type of the differential equation. So x y prime equals y prime logarithm over y prime over x. And again, the differential equation of the first order of the second order, and here we don't have the zero derivative, so we will just so we will use parameter. So p equals y prime, then p prime equals y prime twice. So now substituting into this equation. So x p prime equals p logarithm of y or logarithm of p over x. And actually this so we received the equation. So this is the homogeneous equation where we divide it by x, and we will do the following substitution. So u will be equal p over x, then p equals ux, so p prime will be equal ux u prime x plus u. So making one more substitution. So u prime x plus u equals u logarithm of u. Then let we so now we received the equation with the separable variables. So let we do it. Let we separate variables and integrate. So let we first of all move u into the right part. So then received that du over this expression equals dx over x. So now we will integrate both parts of this differential equation. So this integral just equals a logarithm of module x plus logarithm of c of c1. Okay, let we first of all write down just c1, and maybe if it will be helpful, we will change to a logarithm of c1. So now, what do we have? So let's integrate this expression. Such integral looks complicated, but let we simplify it. So first of all, we will a little bit modify, so transform this expression. We will just factorize. And now what we actually see. Here we will use differential entry technique. So differential of what we have. So differential of logarithm of u minus 1 equals du over u. So we have logarithm of u minus 1. But yeah, module, of course. Okay, let it be logarithm over of module c1 here. We really need it in such case. So let's write down the for inequality. So this one. And now, so now let's simplify it. So c1 x equals logarithm of u minus 1. So what does actually logarithm of u? So what reminding you that u is the substitution. So we need to express here p over x. So c1x plus 1 equals logarithm of p over x. So p over x equals e in power of c1 x plus 1. So, and then p equals x by this exponent. And reminding you that p is not the function that we have to find, but its derivative. So to find y, we will integrate this expression. So y will be equal the following integral x e in power c1 x plus 1 dx, and it will be integrated by parts. So u equals x, du equals dx, dv equals this exponent by dx, then v equals 1 over c1 exponent. So now what do we have now? So now let's start integrating. And here minus integral of this expression dx. Yeah, let me move 1 over c out of the integral sign. So receiving this expression minus 1 over c1 square exponent and plus c2. And now let we simplify it a little bit. So I will move 1 over c out of brackets, and exponent will be moved out of brackets as well. So what do we here have? What do we have here actually? So x minus 1 minus 1 over c1 and plus c2. So the final so the generic answer will be the following. So we found it. So in this case, we were lucky to find it explicitly. Any questions about this exercise? Okay, if no questions, let's move next to the next integral, to the next differential equation. So 1e exercise, and we have the following differential equation: y1 plus y prime square equals to y prime twice. And what do we have here? So actually, this is this is the differential equation of the second order, and we have all derivatives in this equation, but no x. So I mean, so derivative of 0 over the 0 order, the first order, the second, but no x. So we will use here the following substitution. Again, we will use parameter, but y prime will be equal p that depends on y, not on x. Then y prime will be equal, dp by dy multiplied by dy by dx. So how to simplify this expression? Actually, dy by dx equals p. So I have p by dp by dy. So now let we substitute this so new variables into the equation. So 1 plus p square equals to y and multiplied by this expression. So we received the equation with the separable variables. So now let we separate variables and integrate. What do we have here? So moving okay, so first of all, moving this part into this part to the left. No, to the right. So what do we receive? That dy over y equals 2dp 2p dp over 1 plus p square. So let's integrate both parts. And what will we have? So logarithm of module y plus logarithm of c1 equals logarithm of 1 plus p square. Okay, let we move this equation to the next line. So with the simplifying it, we receive that c y c1 y equals 1 plus p square. And actually, yeah, so what do we have? That y prime square equals cy1 minus 1. So now we will integrate this expression, but first of all, we need to, of course, to extract the explicit expression for y prime. So y prime will be equal plus minus this square root. So the square root of this expression. So y equals plus minus the following integral. Stop. Yeah. So made a mistake a little bit. Yeah. So actually, why? So we have. Yeah. Let's separate these variables as well. So here divide by dx. And then we will separate variables and integrate. So dy over this square root equals plus minus dx. And now we will integrate. Okay. So actually this integral will be equal x plus c1. And what about this integral? So let's calculate it with using table of integrals actually. So it will be 2 c1y minus 1 to two square roots of this expression. And yeah, divided by c. 2 over c1. And now let's express y explicitly. So equals plus minus x plus c2. Okay. So what now? Actually, it doesn't really make sense now to okay, we'll not waste the time for integrating now, or I mean, for expressing y explicitly. But now let we solve one more differential equation. So how to do it, you already know. And I see that it's time for a break, but let's solve one more differential equation, and after that we will have a break. Maybe any questions about this exercise? Okay, if no questions, let's move next. Y 2 primes, y, so y prime twice plus 2 over 1 minus y prime square equals 0. So again, we have the same type of the differential equation. So here is no x, but only y of the 0 order, the first and the second. So again, doing the same substitution. So y prime equals p from y. Then y prime twice equals so dp dp by dy and multiplied by dy, so dy over dx. So it will be equal p by dp over dy. So substituting it into the initial differential equation, p square and equals 0. So again, this is the equation with the separable variables. So let we separate these variables. So what will we have here? Yeah, by the way, we will first of all reduce power of p here. And after that, let's move everything out of so let's move to this part. Yeah, and actually it can be written as y minus 1, and we'll remove minus here. And now continue separating variables. So to dy, and here will be p. And now we can integrate both parts. So what we'll receive, logarithm of module p equals 2 logarithm of y minus 1 plus logarithm of module c1. So let we simplify it again. So p equals c1 y minus 1 square. Now, yeah, we remember that p equals the derivative. So uh, now find it. So writing down that dp by dy equals this expression. And now let's separate variables and integrate. What do we have here? So dp equals uh, this expression. Oh, stop. Dy by dx. So dy over dx. Yeah. So what do we have here? That dy over this expression equals c1 dx. So now it's correct. So now we will again integrate both parts of this equation. So this integral will be equal minus uh, minus y minus 2, minus 1, yeah, and minus here. Or we will just rewrite it as 1 over 1 minus y. And this, of course, will be equal x. X plus c2. So let's do like this. So now received the following equality. And now we will express y explicitly. So in this case, okay, we have a little bit time, so let's do it. So 1 minus y equals 1 over this expression. So then y equals 1 minus this expression. So 1 over c1x plus c2. So this is the general solution of the given differential equation. Any questions about this exercise? Okay, if you don't have questions, let's have a break for 5 minutes, and after that we will continue. So we will solve Cauchy problems. Okay, let's continue. So it was a little bit longer, but uh, nevertheless, we have enough time. So uh, now we will solve Cauchy problems. Actually, we will do the analogical stuff as we did in task one, but we will also have to find the partial solutions of the specified equations under given initial conditions. So to A, we have the following equation: y prime twice equals uh, y prime over x plus x square over y prime. And initial conditions, yeah, pay your attention that always number of initial conditions equals the number of equals the order of the differential equations. So here we have the order, so the second order of the differential equation. So it means that we have two initial conditions, and one for y and the second for y prime. And it always must be in such way. If not, it means that some mistake in the task. So, uh, how to solve this equation? As we can see, we have no variable, so just y, function y in this equation, so no zero derivative, so we can do the substitution p equals y prime. So then p prime equals y prime twice. So p prime equals uh, p over x plus x plus x square over p. So received the following equation. Actually, what they what is so what the equation we received? It is it's Bernoulli's equation. So we have p1 prime. So p prime in power of 1. We have here p in power of 1, so it is a little bit similar to linear equation, but we have also this part. So where p equals, so has another power, and in this case, power of 1, power of minus 1. So it is Bernoulli's equation, and let we solve it using Bernoulli method. So it will be product of functions u and v. So p prime will be equal u prime v plus u v prime. So let's substitute it into the initial equation. Not the initial equation, but this equation for p. So we have uv over x plus x square over uv. Now let's move this addend to the left. So reminding you the Bernoulli's method, how it works. So we will move it to the left, and then we will move function u out of brackets. So out of brackets here. So we will factorize this expression, and according to Bernoulli's method, this expression will be equal to 0. And then this expression, so u prime v will be equal x over x square over uv. So now let's solve this equation. Let we find v first of all. So v equals dv over dx. equals v over x. So then dv over v equals dx over x. We'll integrate both parts. Logarithm of module v equals logarithm of module x. And then v equals x. So found v, and now let's solve this equation. So we will find u. So substitute in the v that we received. So here x, and here x as well. So now we will a little bit simplify this equation before integrating. So here just x, and now what I will receive here, so u prime x equals 1 over u. And now let's separate variables. So separating variables, and what we will receive. So du over u equals dx. Oh, stop. Not no. U du equals equals x equals dx. So 1 over 2 u square equals x plus c1. So found it. So then u equals square root of the following expression. Okay, let me move it a little bit lower. So 2x multiplied by x plus c1. And here I have the following, so the square root. So u equals this expression. Then what does p equal? P equals yeah, by the way, so yeah, so okay, let's write down first of all p. Yeah, p equals x by the square root. And then y prime equals x by this square root. And what do we have now? Yeah, first now let us find c1. So using this initial condition y prime from 2 equals 4. So as y prime from 2 equals 4, we have that so 4 equals 2 square roots of 2 plus c1. Okay, and from this equation, with respect to c1, we have that c1 equals 0. So yeah, I have 0 here. So I will receive 4 under the root, so it will be equal 4 equals 4, so C1 equals 0. Then y prime equals x by 2 square root by square root of 2x. And now let's find the y. So y will be equal this integral, so dx. Yeah, let us move square root of 2 out of brackets. And what we will receive? So square root of 2, 2 square roots of 2 divided by 5, x square, square root of x, plus c2. And now we will find c2 as well. So y from 2, let me look what does it equal. So y from 2 equals 0. So y from 2 equals 0. So we have the following expression. So 0 equals okay, and let us substitute here 2. So 4 square roots of 2, so plus c2. So then what do we actually have? So c2 equals minus this expression. So then c2 will be equal. Okay, let us calculate. So 2 by 4, 8, and here will be 2, so minus 16 over 5. So the final answer, so the partial solution will be the following. So this expression minus 16 over 5. So found it. Any questions about this exercise? Okay, as I see, no questions. So now let's move to the next exercise, 2b. So we will receive the following different. So we have the following differential equation: y prime twice equals y prime in power of 2, y prime square minus y prime cube. Yeah, and by the way, initial conditions. So y from 1 equals 1, and y prime from 1 equals minus 1. So here we have the following situation. So we have all orders of derivatives, so including 0 order, but no x. So we will do the following substitution: y prime equals p from y. Then y prime twice equals dp over dy multiplied by dy over dx. So it will be equal p multiplied by dp over dy. Okay, substituting it into the differential equation. So what do we have? Y p equals p square minus p cube. let us reduce the power of p, first of all. So reduced. And now we will uh, uh, separate variables. So what do we have? So dp over p minus p square equals dy over y. So calculating this integral, and we will receive a logarithm of y plus a logarithm of c1. Then calculating this integral. So what about okay, yeah, first of all, let us uh, uh, use the method of undefined coefficients for integration. So yeah, we have the following integral p minus 1 over p minus p square. So we will expand this fraction by simple fractions. So a over p plus b over 1 minus p. So here I have a over a multiplied by 1 minus p and plus bp divided by this expression. So let us regroup the regroup coefficients. So minus a plus b by p and plus a. So we received the following system for coefficients. So minus a plus b equals 0 and a equals 1. So so now we can see that so a equals 1 and b equals 1 as well. So the integral will be the following. So 1 over p plus 1 over 1 minus p dp, and it will be equal logarithm of module p minus logarithm of module 1 minus p. So received the following equality. And after removing logarithms, we received that c1y equals p over 1 minus p. Then, how to solve it? How to solve next? Actually, we cannot express y prime explicitly here. So actually, we cannot do anything for now in this case. So Yeah, it is difficult to move next because of such a situation. So here is no chance to express y explicitly. So then we will just leave it like this, or in a parametric form. So if we vary parameter, we will receive some answers. But now we will have just uh, so we will receive just this answer. But yeah, maybe we can simplify something a little bit. Okay. Yeah, we actually can find C1. C1 can be found. So uh, uh, actually, yeah. So if we substitute 1, so y from 1 equals 1, and y prime from 1 equals -1. So +1. So here we see that C1 equals -1/2. So received the next solution in the parametric form. So -1/2y equals p over 1 minus p. And actually, that's all what we can do now here. Maybe any questions about this exercise? Okay, if no questions, let's have a break. So I will stop sharing screen and I will stop recording. Let's have a break for 10 minutes, and after that we will move to the next practical lesson. So maybe we will finish earlier. Now I will pause the